Hi, good morning students. Today we are going to derive Einstein's photoelectric equation. Before that, you must have studied what is photoelectric effect. The emission of electrons by certain metals when radiation such as visible light or ultraviolet light is incident on them. You must have studied the definitions like threshold frequency, stopping potential, work function in the earlier class. Now we are going to derive Einstein's photoelectric equation. This is derived on the basis of which theory of light? There are different theories of light, is it not? Corpuscular theory of light, wave theory of light, Maxwell's electromagnetic theory of light, and Max Planck's quantum theory of light. So among these four theories, which theory is used means it is quantum theory of light. So I will write here quantum theory. So according to the quantum theory of light is considered to be made up of discrete packets of energy called quanta or photon. So this is the quantum theory of light. So according to this, the energy of a single photon or a single quantum is given by E is equal to h nu, where h is Planck's constant, nu is the frequency of the incident radiation. The theory you must have studied already. Okay. So quantum theory is used to derive the photoelectric equation. Okay. Then according to this Einstein's theory, when light is falling on the metals, when light is incident on metal, what is actually happening? There is an interaction. Okay, there is an interaction between the incident photon. So interaction takes place between the incident photon. You can see here, these are the red color dots are the incident photons. When they fall on the metal, no, the outermost electrons mainly will be interacting with the photons. So between the incident photons and the electrons, okay, incident photons and the metal electrons. So this type of interaction is taking place. As a result, what is going to happen actually? A part of the energy, a portion of the energy of the incident photon is given to the electron for what? To remove the electron or to liberate the electron from the metal atom. Now you can see, my dear students, you can see this is a metal atom. Say for example, if this is a metal atom, there is a positively charged nucleus at the center of the atom, and say for example one particular electron E is bound to the nucleus. The nucleus is exerting a Coulomb force of attraction on the electron which is revolving around it. As a result, there is some binding energy between the electron and the nucleus. So it is not easy to remove the electron without supplying the energy. So some minimum energy is required, is it not? Depending upon the orbit, at what distance is the electron from the nucleus. So the outermost electron or the other shells also, some minimum energy we have to give it. Then only the electron can be liberated from the metal atom. Then for that, who is supplying the energy in this process is the incident photon. So the photon's energy is E is equal to h nu. A fraction or portion of that energy is given to liberate the electron just to come out of the metal atom, and the remaining energy only is imparted as kinetic energy to the electron. If the minimum energy required to remove the photoelectron itself is very large means, then naturally the electron has to come out with less kinetic energy. So this is the consequence of law of conservation of energy. So my dear students, the photoelectric effect is mainly due to what reason? Due to the interaction between the incident photons and the metal electrons. So what is the incident energy we have seen? It is h nu. And now I said that this energy h nu is utilized in two ways. So E is equal to h nu. This is utilized. It is utilized in two ways. Two ways. Okay. One is what? To liberate the electron. To liberate the electron. Okay. To liberate the electron. From where? From the metal surface or from the metal atom. So naturally, the remaining amount of energy only must be imparted to the electron as kinetic energy. So this is to impart, okay, to impart kinetic energy to the electrons, which are called as photoelectrons. So this is the theory you must have studied in the previous class. So my dear students, the incident energy of the photon E is equal to h nu is utilized in two ways. A part of the energy is utilized for what purpose I told you? Just to liberate the electron from the nuclear influence. This is called as work function. Okay. So this is called as work function. You must have studied in the theory. In the introduction class, I have taught you what is work function. That is the minimum energy which is required to liberate the electron from the metal atom. That is called as work function, and that also is denoted by the symbol phi naught. In some textbooks they are using the symbol capital W for work function. In our textbooks, no, CBSE as well as some state boards also, they are using the symbol phi naught. Okay, my dear students, now the remaining energy is used for what purpose? To impart kinetic energy to the photoelectrons. So kinetic energy, if m is the mass of the electron and v is the velocity of the electron, the usual symbol, okay, if you use means, then half mv square is the kinetic energy. So by the law of conservation of energy, I can write the incident, that is the incident energy h nu is equal to phi naught plus half mv square. So this is the first equation. Have you all understood? You tell me. Okay. So h nu is equal to what? Phi naught plus half mv square. You can look at the picture on the board. I have drawn in such a way that the electrons are coming independently without colliding with each other. Normally what may happen when more number of photons are incident, for every single photon, one single electron only will be emitted. In the previous class we have studied that there is a relationship between the photoelectric current and the intensity. So intensity means what? Number of photons incident per second. And current means what? Number of photoelectrons liberated per second. Both are equal. Therefore, for every single photon, one single electron will be liberated. If the emitted electrons, when they come out of the metal, if they are overcrowded, means in random directions if they come, there is a chance for colliding with each other. So what happens during each collision? The electrons may lose their energy. Is it not? So their kinetic energy may be reduced. But now I am going to assume as if the electrons are not colliding with each other. Understand? So if there is no collision, if there is no collision, if there is no collision means do the electrons lose energy? No. So their kinetic energy will be maximum. And this maximum kinetic energy is denoted by the symbol Ke max. So this is equal to half m into V maximum square. Understand? When will the kinetic energy of the photoelectrons maximum? When they do not collide with each other. So in the first equation I am going to write half mv maximum square. So now what is happening? H nu is equal to work function phi naught plus half mv square maximum. So equation 2. Have you all understood how we have got equation 2? By assuming there is no collision among the emitted photoelectrons. So the kinetic energy is maximum. Also, my dear students, we have studied that, okay, we have studied that the work function phi naught is equal to h into nu naught, where nu naught is called as a threshold frequency. Do you remember in the previous class I have taught you what is threshold frequency? So for photoelectric effect to take place, the incident energy should have a minimum frequency. Okay, that is called as threshold frequency. So this since we have already studied, I am substituting here. So phi naught can be replaced by what? H nu naught. Therefore now H nu is equal to H nu naught plus half m v square maximum. Okay, students. Now this H nu naught I will shift to the left hand side, so that it will become what? H nu minus H nu naught is equal to half m v square maximum. Now in the left hand side, which is a common factor, is what? Okay, this is a H. So H into nu minus nu naught. So this is equal to half m v square maximum. What is the relationship between frequency, wavelength and wave velocity? We have studied C equal to nu lambda, where C is the velocity of the electromagnetic radiations. So C equal to nu lambda means what should be nu equal to then? C by lambda. So I can also substitute here H into C by lambda minus C by lambda naught. So this is equal to half m v square maximum, or okay, or Hc into 1 by lambda minus 1 by lambda naught. This is also equal to what? Half m v square maximum. So all these, see, this is equation 3 I can write, and this is equation 4. All these starting from equation 1, 2, 3, 4, all are called as Einstein's photoelectric equation only. Understand? Now, for this derivation, for deriving this photoelectric equation, in the year 1905 he derived. Understand? He explained this derivation. Okay, it was derived in the year 1905, for which along with the theory of relativity he was awarded the Nobel Prize in the year 1911. But this equation was verified by several scientists, and one very popular experiment called Milliken's experiment. Okay, Milliken's experiment, using an experiment, R.A. Milliken derived the same equation experimentally. And for that, what is the kinetic energy of the electron? It was taken that half m v square maximum, half m v square maximum is equal to the work done in stopping the electron. Therefore, it is the stopping potential E into V naught. So Milliken has substituted this half m v square maximum is also equal to what? E into V naught. So E into V naught is equal to Hc by lambda minus Hc by lambda naught. Okay. So what is V naught is equal to, was verified by Milliken. Therefore V naught is equal to what? This small e is taken to the right hand side. So this is equal to H into C is a common factor. Okay. H into C is the common factor. This is 1 by lambda into E minus 1 by lambda naught into E. So like this also we can derive this equation. So actual photoelectric equation is over by the step number 4. In addition to this, in our textbooks, it is given that Einstein's equation was verified by R.A. Milliken. And this equation also you can take this C inside the bracket, and also you can write C by E lambda, C by E lambda naught also. Okay, students? So this is the Einstein's photoelectric equation up to step number 4. If you write in the exam, that is enough. Verification by Milliken you did not mention along with this, but still you must remember, suppose in the competitive exam they ask means this equation also can be substituted. Have you all understood, students? Shall we go to the next video? Fine.